The characteristics of the atmosphere can be recognized in many ways. The first way that most scientists start to examine the atmosphere is through the atmospheric profile. When we think profiling, we think of the characteristics of individuals for the most part. Where do you work? What do you look like? What are your hobbies? That sort of thing. Well, the atmosphere can be examined the same way. It's got multiple different components that can be profiled. When most scientists ask or talk about the atmospheric profile, they're referring to what the density of the atmosphere is. And we find that the atmospheric density is greatest closest to the surface of the Earth and decreases almost uniformly out to the edge of the atmosphere and then before you reach the exosphere or outer space. The volume of matter in the atmosphere at a particular location is recognized as the amount of pressure exerted in all directions onto a body. So the greatest volume of pressure correlates with the greatest amount of particulate matter and gas matter in the atmosphere at a particular location. At sea level, that pressure is 1,013.2 millibars. So think about 13 pounds per every square inch. That pressure decreases as you go up, and if you go below sea level, there are some areas that are lower than sea level, then that pressure is going to increase. 90% of the total composition of the atmosphere extends from the surface of the Earth to about 10 miles up. So that would be equivalent to driving from Youngstown into Niles. Towards Warren. So it's not really deep at all. That's a significant amount of matter within a short spatial area or distance. The remainder, or the next almost 10% of the rest of the atmosphere, extends from 10 miles through to about 31 miles. So it becomes quite empty above 10 miles in height. So this is what we've got for our atmosphere. The volume of matter in the atmosphere is critical because it relates directly to the capability to store energy in the atmosphere. When photons come in and they hit a particle or a molecule in the atmosphere, it's going to transfer some of that energy to that particle. Depending on what that particle's characteristics are, it's going to absorb some volume of energy and store it. It's going to re-radiate some of that energy, and that photon of light will be headed in a different direction at a slower speed, rendering it less harmful if it was a harmful photon of light, UV light, maybe X-ray. And what is retained in that molecule that was impacted by that photon of light is going to at some point re-radiate that energy, and that re-radiation of energy can be measured as a heat unit, how much energy there is available. So consequently, the more matter you have, the more energy can be stored. The more energy that can be stored, the more energy can be re-radiated as heat. So functionally, down where the molecules are the densest, the greatest volume of heat is. And as you move up through the atmospheric profile, logically, one would then assume that the temperature decreases as you move up. It should also be noted that all bodies radiate energy. Our sun is a primary radiator of energy. All other matter that sunlight encounters is a re-radiator of energy. So the desk that you may be sitting in front of is absorbing sunlight and will re-radiate that. These sorts of things are most apparent during the day. When you're walking across concrete in the summertime, perhaps barefoot, you're going to realize that the concrete is exceptionally hot. You can feel that heat on the bottom of your feet. That's re-radiated energy from the concrete that was collected by the sun. At night, that concrete feels cold because the concrete has very low capacity to store heat. It's going to release it right away, so the temperature is going to be hot. Water, on the other hand, has a high capacity to store heat. So it may store the same volume of heat as the concrete did at, as measured, but it's going to feel cooler than the concrete because its storage capacity is greater. It's going to feel warmer later than the concrete because it's still re-radiating the energy that it collected, where the concrete was not able to store it and it gave that energy up right away. Other ways that the atmosphere can be characterized are through its thermal layers. So how much energy occurs at different layers of the atmosphere. We measure that as proxy measure of heat, how much heat is in different parts of the atmosphere. We can measure that as functional layers and compositional layers. I'm going to combine functional and composition together because I think that it's easier to appreciate what the composition allows the atmosphere to do. So I'll be delivering those together. So with the thermal layers, what we find is initially true that the bottommost layer, which is the troposphere, which has the most amount of molecules, is the hottest of all of them, and that the thermosphere, which has the fewest amount of molecules, has theoretically the coldest temperature. And we're going to get to that because if you're taking a look at the graph, you're probably going to say to yourself, wait a minute, the temperature's going up in the thermosphere. So let me back up quite a bit here. Each layer is measured or recognized for whether or not that part of the atmosphere is heating or cooling. We know that as you go up in the troposphere, the lowest layer, that the temperature is going to decrease with an increase in elevation, and it continues to decrease because the volume of matter is decreasing, so the storage capacity of energy and the re-release of heat is less. It's going to do that until we get to the tropopause. At the tropopause, the temperature changes direction. As you go up in elevation, the temperature increases, even though the volume of matter is decreasing. So that doesn't make a lot of sense, but we've got to recognize that in the stratosphere, where this is occurring, houses the ozone layer. And the ozone layer does a couple of things. One, as photons of light are coming in and they're hitting the ozone molecule has a great capacity to store volumes of heat and re-radiate them. So we're heating this part of the atmosphere up because of the presence of the ozone layer. The other thing that O3 molecules do is re-radiate that energy into different directions. So that initial photon of light that was coming towards the surface of the Earth gets bent, and in some cases it gets bent and it strikes other molecules of ozone and other molecules of other compounds in the atmosphere, causing them to heat up. So we get this stratosphere of increased warming with increased elevation because some of those photons are headed back out towards outer space before they hit another molecule. So the stratosphere is a zone of increased heating because of the existence of the ozone layer here, despite the fact that the volume of matter is decreasing with elevation. That trend of heating terminates at the stratopause. At the stratopause, then we enter the mesosphere, and at the mesosphere, we return to what is considered a condition of normalcy, where we have decreased volume of matter, less holding capacity because there's less matter. So the temperature is going to decrease with elevation through the mesosphere until we get to the mesopause. At the mesopause, then, we get a slight static temperature with elevation and then a marked increase of temperature. But it's not temperature, it's energy. We have a great volume of energy in the thermosphere. We've got lots of energy coming in. They're at their highest frequencies that are coming in, and there's very little matter to get in the way. Remember, this is the thinnest part of the atmosphere, so these photons aren't going to strike a lot of particles at this place. So high energy environment, but until you hit a particle that is going to store some energy and then translate it into heat, we're not going to have any heat. So the temperature here is low, but the energy content is high. So anytime an atom or particle is struck with a photon of light, we're going to store a lot of energy, but we're going to release that energy really fast. So the heating units are going to be exceptionally localized in the thermosphere. Above the thermosphere is the exosphere, and exo is external. That's outer space. The next two layers that we can consider defining the Earth's atmosphere by are composition and function. And composition is going to determine function. However, the function is the same regardless of where what we're talking about in terms of location. And the atmosphere's function basically is to protect and shield the Earth from the solar wind that's coming into it. The textbook doesn't talk too much about the magnetosphere. It goes right into the ionosphere and the ozonosphere. But I want to start out with the magnetosphere because it's the magnetosphere which is the first element that shields the planet from these solar winds that are coming from the sun. And this magnetosphere is generated by the internal gyrations and the electrostatic energy that is occurring in the center of the Earth because of the rotation of the Earth. It's expelled at the poles, and then we sort of turn our planet into this large bar magnet. It's this outer bar magnet, and the highly charged hydrogen and helium atoms at the very edge of our atmosphere that shield the planet from incoming solar radiation and act as a foil and deflect most of that solar radiation out around our planet, only allowing a very small portion of that energy to actually penetrate through the magnetosphere into the ionosphere. Once those particles or those photons enter into the ionosphere, again, very thin environment here of matter, what does get intercepted by the hydrogen and helium at the highest elements start to slow down those fastest wave particles coming through, and eventually makes them less and less harmful as they penetrate deeper and deeper towards the surface of the Earth. So really important here. Those shortest waves are cosmic, gamma, X-rays, and UV radiation, and they should be, with every impact, lengthening out and becoming less harmful. So by the time they hit the stratosphere that houses the ozone layer, most of those fastest particles are now much slower. Now, sometimes much slower means they've become UVA, UVB, and UVC wavelengths, and those are still exceptionally harmful. So we need to translate those into longer wavelengths, and that's what the ozone layer does. Is it allows those to be lengthened even further. So those O3 molecules, when a photon of light hits them, they're going to vibrate. They're going to collect some of that energy. They're going to create a bit of a force field through their own motion that was generated by the exception of some of that photonic energy, and create a bit of a force field and occupy more space, allowing the ozone layer to deflect more and more of that energy, which is heading towards Earth. Eventually, most of the shortwave energy is converted to longer, safer wavelengths to include visible light rays. So all energy is coming in through the electromagnetic spectrum. So these are those photons of light. And solar energy comes in from the shortest wavelengths, the gammas, wavelengths through to the longest wavelengths in the electromagnetic spectrum. And as they go deeper and deeper towards the surface of the Earth, we're going to then lengthen those out. So I will let you read through this at your own pace. Most of it I've covered already. And I will start the next slide set with the Aurora Borealis.